We have the means. Now we need the will. Thank you.
Thank you so much, Karen. We're now going to move over to my colleague, Rachel Traharn. Yes, so Rachel's a scientist at the Woodwell Climate Research Center. She's an Arctic ecologist studying disturbances in northern ecosystems with a particular interest in abrupt and difficult to predict processes. Rachel is a member of our Arctic program, and she's going to speak today about her work. Thank you, Rachel.
Thank you so much for the introduction, Dave. I'm absolutely delighted to be a part of this panel, and thank you so much to all of you who've given up your time to join us virtually for this event. We're going to be moving now from the sea onto the land in the Arctic, and I'd like to invite you to just take a moment to imagine that you're standing in the environment in this photograph on the first slide. And I'd like you to think a little bit about not the sort of the plants or the animals that you might be looking at, but to think for a moment about what would be under your feet. And the answer to that question is this really quite shallow layer of soil which is frozen in the winter and then thaws during the summer. And below that is what we call the permafrost. So this frozen portion of the ground that remains frozen year on year. And the first thing that I'd like to say about the permafrost and about permafrost thaw is that this is not a kind of possible future. Permafrost thaw is very much a current and very tangible reality across the Arctic, and it's something that is having huge impacts on the 5 million people who live across the Arctic today. Unfortunately, we know that those impacts are also going to continue and are going to increase. As Dave already mentioned, the Arctic is warming incredibly fast. This graphic created by my colleague, Greg Fisk, this is showing mid-century projections of warming around the world as elevation. And what this highlights so well is that really disproportionate rate of warming that we're seeing in the Arctic. So the Arctic is warming indeed 3 times faster than the global average. And this rapid pace of warming and its implications for permafrost is something that has consequences across the full Arctic region. So this graphic that you're looking at is showing the current extent of permafrost across the Arctic and the boreal zones in that really pale red color. And then you're looking at the projected sort of remnants of that permafrost extent in 2050 and 2070 in the darker red colors. And you can see that we're looking at a really substantial expected loss. And to put that into numbers, what we're looking at here is that we expect to lose something between a quarter and almost 3/4 of all of that near surface permafrost. That's permafrost in the top 3 meters. And of course, that's also a really broad range. And where we fall in that range depends very much on the mitigation effort that we make in the meantime. So, as I mentioned already, this is something that is having already these very, very tangible and very far-reaching impacts for Arctic communities. But this is also something that is important to all of us around the world. And the key reason for that is that permafrost is an absolutely vast carbon store. So permafrost covers less than 1/4 of the Earth's surface, and in that relatively small area, it holds almost twice as much carbon as there is in the atmosphere today. So that's more than twice as much carbon as there is stored in all of the trees across the face of the planet. As the Arctic warms, as we've already seen, and of course that permafrost warms and begins to thaw, what this means is that carbon becomes vulnerable to decomposition as all those microbes start waking up and start becoming more active. And that means ultimately that carbon can be decomposed and can be released back into the atmosphere, either as CO2 or as methane. But permafrost thaw is not just one process. There is a lot of complexity here, so we're going to take a moment just to unpick a little bit of that. And actually, when we use the phrase permafrost thaw, often what we're actually talking about is gradual permafrost thaw. So you're looking at a representation of that process here. So what we're talking about is this kind of gradual top-down process where the air is warming and the ground is warming, and you see centimetre by centimetre, year by year, the permafrost thawing at the top and just getting deeper and deeper and deeper. And this is the dominant source, really, of permafrost thaw, but it's not the only way that permafrost thaws. So we also see abrupt permafrost thaw. So this is actually an umbrella term for a whole range of very different processes. But what we're talking about here is, of course, those more kind of abrupt thaw processes. Often this is something that happens when we have ground which contains a lot of ice, and as that ice thaws and we lose that water, we see the uneven subsidence or even the collapse of the ground. And this is the kind of processes that we're looking at when you see pictures like this one here of these really large-scale, quite dramatic landscape features. And this isn't the end of the story for permafrost. Something that we are all hearing more and more about in the news, especially over the last couple of summers, is fires across the Arctic and across the boreal zone. Fire is an important part of these ecosystems, but we're seeing really, as warming continues, those fire regimes becoming more intense. We're seeing fires happening more frequently and being more severe. And those both liberate carbon directly during the fire, actually by primarily by burning the ground and liberating carbon directly that way. But they also have a really important impact on permafrost. And I think you can see quite clearly why that is the case from this picture here. You can see that after a fire, not only have we lost the vegetation, but we've got this real darkening of the ground surface. And of course, that means that ground is absorbing more heat and sort of conducting that heat down towards the permafrost. And so this is something that accelerates and even initiates both gradual and abrupt thaw. So the reason I'm talking you through these processes is that this is something that really creates a big challenge for us as scientists when we're trying to estimate how much carbon will be lost from the permafrost. So that complexity makes that a real challenge. And that challenge of these kind of complex processes is really exacerbated by the fact that we really don't have the data that we would like to have across the Arctic. You can really imagine why that is. This is a huge region. It's very variable, even at quite small spatial scales. Of course, we have the complexity in those processes that we've just talked about. And it's a relatively sparsely inhabited region. It's often, parts of it are quite inaccessible. It's a difficult place to work. And this image here is really showing the consequences of that. So the little dots across the Arctic highlight monitoring sites where we have all year round monitoring of CO2 and methane fluxes. And you can see there are vast areas of the Arctic that really have almost none of that monitoring happening. The result of this, of the challenges that I've mentioned, is that right now very few, a tiny minority of climate models include any consideration of permafrost carbon at all. And those that do include only gradual permafrost thaw. So there are no climate models at the moment which include those abrupt permafrost thaw processes or which include the relationship between fire and permafrost. One of the things we're working on at Woodwell right now is to try and take some steps towards changing that. So to do that, we're working towards building some of these processes, so abrupt thaw processes, emissions from below ground combustion, and the interaction between fire and permafrost thaw into what is essentially a simplified climate model. And this is something that it's very much work in progress. There's a lot more work to do. Of course, I've mentioned some of those challenges associated with that. But of course, we wanted to give you a little bit of a flavor of what the eventual outcomes might look like. And so what you're looking at here is one kind of potential, one possible future of emissions from gradual permafrost thaw. So you're looking at those emissions over time from around the present day out to the end of this century. And this is under a pretty moderate warming scenario, so RTP 8.5. And to sort of build on this, if we rerun that updated climate model and we look at those emissions over the same time period for abrupt thaw and fire-related processes, then we're looking at something like this. So something that really is itself on the same scale as those gradual thaw emissions. And even when we look at a much more extreme warming scenario, RTP 8.5, where we know that we expect to see much more widespread loss of permafrost through gradual thaw, we still see that those processes, which again are not yet accounted for in any climate model, are operating on the same scale. And just for a little bit of context here, that little red star on the left is approximately EU emissions from 2017, and the little red star on the right is the emissions from the US, again in 2017. So really what this means is that if we continue to leave these processes both out of our climate models and out of the debates about future climate, about future sources of emissions from the Earth system, we are essentially doing something equivalent to ignoring a major economy by the end of this century. So what does this mean for all of us here at COP this week and next week? Clearly, the key message is that we need immediate and ambitious mitigation action. It's critical that we minimize the emissions that we're seeing from what is a very rapidly warming Arctic. And really what these processes tell us is that we all know that that window of opportunity to keep to the Paris Agreement targets is closing rapidly, but actually we have a lot of uncertainty about how much of that window is left, and it is likely to be closing even faster than we think. So we really we can't afford to delay, either, of course, for the communities in the Arctic or indeed for all of us around the world. Thank you very much.
Thank you so much, Rachel, for that excellent presentation. We're now going to move over to Dr. Sarah Das. Sarah is a scientist at the Woods Hole Oceanographic Institution as well. She researches glaciology, paleoclimatology, and the role of the cryosphere in the Earth system. Sarah, over to you.
Thanks, Dave. And it's really an honor to be here, and thank you all for attending this virtual panel today. We've been hearing so far during this panel about all the dramatic changes that are happening across the Arctic. We've heard about many of the changes in the Arctic Ocean and sea ice and ecosystems, as well as the changes on land and the consequences for permafrost. What I would like to share with you today is my area of research, which is in polar glaciology. And that's part of the cryosphere. So I've spent much of my time working on the Greenland ice sheet, trying to understand how large polar ice sheets like Greenland and Antarctica are responding to climate change, how they grow and how they shrink, and how the ice moves from the center of Greenland towards the sea. And I want to start with this image and a caution for those of you in the audience and those of you who are here at COP making decisions for our future. We are running full speed towards the abyss. This is the climate crisis. Outside of COP today, the youth are marching and trying to continue to draw attention towards this crisis. I spend much of my time in the Arctic and in Greenland. I lead many expeditions. Over the last couple of decades, I have spent many years in Greenland. And while I'm there to try to focus on the science and collect observations and try to better understand how Greenland works, I also have a primary goal as an expedition leader to keep my team safe, to look out for hazards, to change our plans if conditions warrant. And I think there's an important parallel between that as an expedition leader and the leaders that we have gathered at COP here this week, the international leaders. We across the world are looking to you as the leaders to keep us safe, to keep us as humanity from entering this abyss, to look out for cautions and to make changes. Sometimes dramatic changes are needed. Dramatic changes are needed to keep the Arctic frozen. So, as I mentioned, I spend much of my time working on the Greenland ice sheet and trying to understand its behavior. One thing that I think is not appreciated enough is that the loss of the Greenland ice sheet is happening in my lifetime and yours in response to global warming, as we've heard already about in this panel, which is amplified 3 times in the Arctic. Over the course of a single generation, we've gone from a stable Greenland ice sheet to one that is rapidly declining. I was born in the 1970s, during a period of time when Greenland was quite stable, as you see on this chart here. So illustrated on the x-axis is time from 1972 to 2018. And on the y-axis is the decline in Greenland ice. So the loss of ice entering the ocean directly contributing to sea level. And what you see is the blue line is quite stable. up until about the early to mid 1990s, and then it starts to plunge, sort of like the abyss we were looking at in the prior slide. So over the course of one generation, from when I was born to when my youngest daughter was born in 2009, we have entered an entirely different world when it comes to the cryosphere, and when it comes to Greenland, and when it comes to sea level. We are now in a world where sea level is rising and is going to continue to rise due to many factors: the warming of the oceans, the loss of mountain glaciers, and increasingly, playing a large role, the loss of the Greenland ice sheet. Greenland is now melting from the highest summit to the coast. You may think of Greenland as remote, as cold, as an icy place, especially in the interior, that can be many kilometers thick. You're probably aware in the news this summer, for the first time in recorded history, rain was observed falling on the summit of the Greenland ice sheet. It should not be raining on the summit of the Greenland ice sheet. It should be very cold and snowy on the summit of the Greenland ice sheet. And there's not a summer now that goes by when Greenland is not in the news, and we hear about another impressive melt event or warming event. In fact, it's become so common that now if there is a cooler than average summer, that itself is making news. Science has clearly shown that Greenland is melting. It's melting more and more rapidly, and it's melting from the highest elevations all the way down to the coastline. Illustrated in the colorful map of Greenland on the lower right is mass loss of the Greenland ice sheet over just the last couple of decades using satellite observations. And shown in the color is the change in thickness of ice. And what you see is the ice is most dramatically being lost around the margins where it's at lower elevation and more susceptible to warming. On the left, you see a cutout section view of Greenland. From the right-hand side is the partial interior all the way to the coast on the left. And dotted across the surface, you see little blue specks. These are meltwater pools of water that form every summer. The far right is a brighter white. This is snow cover. It reflects more sunlight. But this line, known as the ELA, between the darker ice and the blue water and the white snow is moving and marching farther inland year after year. This is another feedback process. The more that Greenland melts, the more susceptible it becomes to future warming and future melt. At the margins of Greenland, we also know that as these glaciers are entering the ocean, they're starting to melt from below, where warmer waters are lapping around glaciers and melting and increasing the capping of ice. So there's many conversations here at the COP26 meeting about temperature targets, emissions targets, and looking out into the future. And I would argue that these goals, like we are trying to set here collectively, must aim to keep the Arctic frozen. You might think there is not a huge difference between a 1 degree or even a ½ degree target, but if you think about ice, it only takes a few tenths of a degree to go from solid ice to water. And so the ice in Greenland and across the Arctic is extremely susceptible and sensitive to these small changes and these small, what may seem like small changes in target emissions and temperature. We know that the Arctic is melting in response to global warming, as seen on the top left chart in the gray line up to the present. But looking forward, we see that under different emission scenarios, we have a dramatic range in future temperatures. And we must take all action to keep these future temperatures rises in check. On the bottom chart, you see Arctic sea ice, another important part of the cryosphere. Again, sea ice is very susceptible to very, very small changes in temperature. It only takes a little bit to nudge ice from frozen to liquid state, and at that point, it's gone. So we return to the plunging blue curve of the loss of Greenland ice over the last few decades. And I've now superimposed on this many of the activities and actions taken by the UN and international bodies in response to the global warming crisis. Beginning back with the creation of the UN Environment Program at Stockholm in 1972, when Greenland was still stable, but we started to recognize the problem that global warming and climate change was going to cause. Through the creation of the IPCC in the late 1980s, numerous conferences, bringing us all the way through to the most recent Paris Agreement in 2015. You might cynically look at this graph and think, well, is Greenland wasting away in response to these actions? But of course not. If not for these actions and these agreements and these targets, Greenland would be melting even more quickly. So in the next slide, I'm going to zoom into just the most recent 2 decades of this rapid decline. What we see here, just from 2002 to 2020, is a continued summation of the loss of Greenland ice. And this line has a little more structure to it, and actually this is representing our ability now, using satellites, to measure the change in Greenland very carefully, the change in mass of Greenland over time. And again, superimposed on top of this, you see recent COP meetings and the beginning towards today of the goals to limit warming. But throughout this period, we still know that ice loss is accelerating more rapidly, and it's increasingly becoming irreversible. It's only with international cooperation that we can slow this decline, and I would argue only within the framework of the discussions here at these kind of meetings that we can make the changes that are necessary in an equitable and just way. And so we look to the leaders that are gathering here this week and the conversations that will continue to make that happen and ensure our future. A lot of our decisions already have committed us to sea level rise. Greenland is responding now, melting, to decisions that we made in past decades through mid-century. There is not a lot of difference in the loss of ice or committed sea level for the next couple of decades. But beyond that point, it is entirely up to us and the choices that we make about our energy future, what scenario we're on in terms of warming and in terms of sea level rise. And of course, the world doesn't end in 2100. Ice will continue to melt as the planet warms. And as you move farther and farther out, as illustrated by the bar graph on the right, we start to see the implications of the fact that Greenland and Antarctica contain meters and meters of sea level, not just the centimeters that we hear about today. I'm going to show you a few examples of some of the work that I carry out in Greenland from the cold interior regions where we collect ice cores and measure changes of past climate. These are areas that should be cold and snowy are increasingly being susceptible to melt. We can use these ice cores as a time machine to look back in time and see how climate has influenced snowfall and melting in Greenland in response to climate. And increasingly, we're concerned that where these pristine archives are collected are melting away. I also work in the areas of Greenland where those blue dots are. These are meltwater ponds, rivers, and cracks. And this water is forming every summer during the warm periods when the sun rises over the Arctic. And this meltwater does not stay on the surface. We now know that it plunges directly through over a kilometer of cold ice to the base of the ice sheet, where it enhances the speed and this ice flows more quickly to the sea. But where does that water go after it reaches the base? It comes out underneath these glaciers into the ocean, where it interacts with the warm seawater and further amplifies the melting and calving. So much of our work is also now focused on these ice ocean regions, where we use new technology and oceanographic techniques to measure ice melt over time. In all of these places, we see that melt is increasing and Greenland is wasting away faster. So I leave you with an important point. What happens in the Arctic does not stay in the Arctic. People on every continent of the world are affected already by rising seas, and they will be through this century and through future centuries. It's only 2 generations between my grandmother and my daughter, and that's 100 years. So if you think out 100 years, it's not really that long. And the differences that happen at 2100 and beyond are entirely up to the choices that we make. And we look here to our leaders to help guide us towards a safe future. Thank you.
Thank you so much, Sarah. We're going to move now to my colleague, Darcy Peter. Darcy is a research assistant in the Woodwell Climate Research Center's Arctic program. She's Gwich'in Athabaskan from Beaver, Alaska, which is located along the Yukon River, and has a firsthand experience and viewpoint on the impacts of Arctic climate change. Darcy, over to you.
Thanks, Dave. So Drin Gwinzi, everybody. Good afternoon. As he said, my name's Darcy. And today I'll be talking about the very real, very sobering on-the-ground impacts of climate change in my personal experience. But before I do that, I do want to give a land acknowledgement and say that Woodwell Climate Research Center is located on the traditional land of the Wampanoag people, which is modern-day Falmouth, Massachusetts. So there are many impacts that permafrost thaw and climate change have, at least in the state of Alaska in the US. Coastal erosion is currently eroding entire coasts of communities, and this is deeply impacting our cultural way of life and our survival, quite frankly. The top left photo is a photo in Kotlik, Alaska. That's along the western coast. The top right photo is in Kivalina, Alaska. You can see pretty clearly that where these villages are is always located by a body of water. Water is a way of life, and it's a lifeline for my people. In the bottom left photo, you'll see a photo of Nelson Lagoon, and those little white dots along the coast are sandbags to protect against coastal erosion. There are two options to protect against coastal erosion. One is protecting in place, which is what Nelson Lagoon has elected to do by placing man-made sandbags along the coast because there's a mass decline in sea ice, as we just learned. And these man-made bags usually are not a viable option. And if you look at the bottom right photo, you'll see a very similar image of these sandbags trying to take the place of sea ice, which is not a viable option, as I said. It increases waste, and it's just not efficient to protect against the elements that are storms and the ocean. In addition to coastal erosion, there's mass flooding. In the photo on the left, you'll see Kwigillingak, Alaska, also located in the Yukon-Kuskokwim Delta in southwest Alaska. You can see that basically the entire village is underwater. No planes can land when this happens. One storm surge can last multiple weeks. In the top right photo, you'll see the village of Newtok, Alaska. You'll see that the boardwalks are our road system when it comes to Western Alaska. And in the bottom right, you'll see Nunapachuk, Alaska, where we do have some field sites, and we're working with that community, also flooding, and this can last multiple days. So it's a very different picture when it comes to flooding. Another thing that's happening in Alaska as a result of climate change is a huge increase in wildfires. In the left photo, you'll see interior Alaska, which is a boreal forest. This is in 2019. This is an aerial photo of a wildfire that took place, and it burned all summer long. People weren't able to go outside and practice their traditional way of life. Wildfire is an increased topic of conversation throughout the entire state. In the top right photo, you'll see a photo of Fort Yukon, Alaska, which is where my dad is from, also in 2019. It was a huge fire season in interior. In the bottom right photo, you'll see a photo of the Yukon-Kuskokwim Delta, which is a tundra environment, and it's usually completely saturated, but there's also an increase in fires as well. So we have flooding and we have fires that are both a direct impact of climate change. These deeply impact infrastructure. And in addition to public health, it's a huge topic of conversation that needs to be had. In the photo on the left, you'll see a house that has since been abandoned in Shishmaref, Alaska, that's falling into the ocean. And in the photo on the right, it's a photo of a house in Bethel, Alaska, which is in the southwest part of the state. And every home is built on stilts for the flooding and for the thawing permafrost that can shift the level and the balance of the home, which they have to rebalance about twice a year, and it's a pretty expensive task. But what I'm going to focus on today is my community of Beaver, Alaska. It's located about 100 miles north of Fairbanks along the Yukon River. There are about 30 permanent residents who live in Beaver. We don't have a grocery store. We don't have very much economic opportunity. We practice a completely subsistent way of life, meaning we hunt, fish, and trap as a means of survival. We get our drinking water from the river. Every animal that we harvest is not for sport. It goes straight into our freezer, and that's what sustains us throughout every season of the year. The picture I'm going to paint, I guess, is going to be the direct tie between permafrost thaw and food insecurity, which is a very common feat in interior Alaska and for a lot of communities along the Yukon River. This is a photo I took in 2020, in the fall of 2020, when I was going moose hunting with my family. And this is very typical of what you'll see along the Yukon River. It's trees falling into the river as a result of thermoerosion, which is erosion as a result of increased temperatures. So the river is therefore getting wider and shallower. And in an area where the river is considered braided, the channels change. And this gets really hard for us to navigate. It's a safety hazard, obviously. And it also makes it very difficult for king salmon to find their spawning grounds. Salmon account for 64% of all protein along the Yukon River, so it's a huge food source to us. And like I said, there's no grocery store in Beaver, so we rely completely on these animals. They are very sacred to us. King salmon are they're an animal that my ancestors have relied on since time immemorial. We're very in tune with our land and our way of life. There are so many graphs and tables that we can see, but to actually see photos of what those graphs and tables mean, I think is a pretty powerful image. And this past year, 2021, is actually the first summer in my life that my community was not able to fish at all for king salmon because there's a mass decline. So the eroding river banks are changing the channels, which is, as I said, making it more difficult for the salmon to find their spawning grounds, which is one of the many factors contributing to the mass decline in king salmon. In addition to physical features that are contributing to the mass decline, there's also the policy aspect as well. So we are the most heavily regulated district along the Yukon River, and we were completely shut down this past year. So since we weren't able to harvest salmon, which is, again, 64% of all protein for people along the Yukon River, we then had to shift our resources towards moose hunting in the fall. In the photo on the left, you'll see that there are, the first way to hunt moose is to go by four-wheeler. Gas is $6 a gallon in Beaver. As I said, there's very limited economic opportunity. So where we direct our resources and where we spend our resources is very important, and we have to be very smart with how we do it. There's another challenge that comes with moose hunting every year, and it's a direct disconnect between climate change and policy. So the amount of time that we're allowed to hunt and harvest a bull moose is usually 1 month out of the year. It's from the end of August to the end of September. And during that 1 month, each person is allowed to harvest one bull moose per person. But during that 1 month, there are maybe only 2 weeks that people are able to efficiently and effectively harvest a moose because there are only 2 weeks now that the moose are in rut, or it's the optimal time to hunt a moose because you can call them, it's very strategic, and this is how we've hunted since time immemorial, as I said. So this is 2 weeks out of an entire year that my people have to fill our entire freezer. We have no salmon, and moose is our only viable option to harvest a large amount of meat. And I know many people in my community who didn't get a moose at all this year. So it's becoming increasingly hard to do that. In the photo on the right, you'll see that the other way to hunt, if not by four-wheeler, is by boat. This uses a lot more gas and a lot more resources. Not everybody in the community is fortunate enough to have a boat. So this just really amplifies the heaviness that comes with hunting a moose. That being said, there are other things that we do. We can go pike fishing in the spring. Pike are not a good fish to eat, for us at least. They are only good in the springtime because they begin to decompose in the summer months. And it's really about community when we go out. This is our way of life that my great-grandparents and their great-grandparents have practiced, and it's been passed down from generation to generation. And so you can kind of start to see the cascading impacts that permafrost thaw has on an indigenous community and on people in the Arctic. It's directly impacting our way of life and our survival and our sustainability. It's something that is really hard to talk about a lot of times in these spaces, and it's something that I believe is really important to talk about. In the photo on the right, you'll see that Beaver is very small, and we take a 6-seater plane to go there, and it's, as I said, it's very tight-knit. Everybody knows everybody. The best part about this is that we're a very resilient people. We are very good at adapting. It might seem very daunting and very unfair, but this is just one of the many things that we have as a people, that we practice, that we take pride in, and that we pass down from generation to generation. My biggest concern is that there won't be king salmon for my children to cut as I was raised. And that to me is very sad, but then I shift gears and I'm like, oh, well then there might be bull moose that we can hunt. So it's all about community, it's all about passing things on from generation to generation. And as a scientist and as an Indigenous person, there are a lot of things that scientists can do to work with Indigenous people. And I see a lot of hope moving forward in the next generation of Arctic scientists in terms of how we can work together and co-develop projects that can benefit Indigenous communities and get them the just answers that we so desperately need. So with that, I'll say masit cho, which means thanks so much in my traditional Gwich'in language, and there's my email. Thank you.
Thank you so much, Darcy. Now we're going to go to an online participant, another scientist from the Woodwell Oceanographic Institute. We'd like to welcome Dr. Rich Camille, who's an associate scientist focused on applied ocean physics and engineering.
Good afternoon. Thank you, David. It's an honor to be here virtually. My work focuses on marine robotics and in-situ sensing for environmental observation. Over the next few minutes, I'd like to focus on a few exciting new technology developments that are enabling better monitoring and understanding of Arctic ice dynamics and associated marine environmental change. As described by the previous speakers, ice coverage is decreasing. The chart on the left shows trends over the past 40 years, and this year we are on track for another record low. But ice coverage is really only part of the story. What else is happening that we can't easily see? The Arctic ice cap is dynamic and one of the most inaccessible regions for humans, so direct observation is challenging. Also, seawater is opaque to most of the electromagnetic spectrum, and this generally limits satellite data to just surface observations, and it leaves major gaps in our understanding of the subsurface. It wasn't until 1958 that the first marine vessel reached 90 degrees north and was able to peer under the ice pack. Note that I said marine vessel and not ship, because it was a nuclear-powered submarine, the USS Nautilus. And during the last half of the 20th century, military subs became a preferred tool to measure ice thickness. Curiously, much of our historical record of ice thickness and its variability was a byproduct of Cold War military strategy. Well, nuclear-powered submarines typically carry a hefty price tag in the range of billions of dollars. And although they don't have much of a carbon footprint, they require hundreds of megawatts of power to operate. And this makes them impractical for persistent environmental monitoring. Fortunately for climate science, over the past few decades, advancements in autonomous robotic technologies, or what are commonly referred to as drones, have enabled us to reduce significantly the cost and complexity of subsea observation. Whether a nuclear-powered military sub or a robotic vehicle, the cost tends to scale with size. And if these systems were sold by the kilogram, they would each cost roughly $10,000 per kilogram. So smaller generally equates to less expensive. If we consider range, this tends to vary inversely with speed, and it works out to be a tortoise and hare type situation. The vehicles in the lower right of this figure travel relatively slowly, but have power utilization typically less than 1/10 of a millionth of the power that a nuclear sub or ice-breaking ship requires. Now, initially, these marine robots were only able to carry out very simple missions, not unlike glorified Roomba vacuum cleaners. But over the years, they've gotten smarter, and smarter translates into more capable. For instance, the various autonomous underwater gliders shown in the lower left inset are now routinely used to identify and track marine mammals as they migrate during seasonal ice advance and retreat. Other vehicles like the AutoSub, which was developed by NOC here in the UK, is incorporating advanced navigation processes that will enable multi-month science missions, including one as it transits underneath the entire Arctic ice cap. The proposed mission path is shown on the right, and Amundsen's historic 1905 Arctic transit is shown for comparison at the left. Through the support of the U.S. National Science Foundation, my colleagues and I at Woods Hole Oceanographic are developing autonomous control policies that also allow underwater robots to intelligently harness ambient environmental energy. This approach is conceptually similar to how spacecraft use gravitational fields to slingshot their trajectories through our solar system. In our case, these intelligent policies can extend our scientific survey range by up to thousands of kilometers. Now, under ice missions are extremely risky, and the probability of vehicle loss sometimes exceeds 50%. So this makes insurance underwriters reluctant to insure expeditions against loss. But as we increase the embedded intelligence of these autonomous robots, they not only become more efficient, but also more capable, less environmentally intrusive, and more likely to survive their mission. One way that my colleagues and I are doing this is by building perception into these robots so that in addition to logging environmental data for scientific investigation, these vehicles can also interpret and assimilate the environmental data in real time to manage their own risk in order to find safe paths in ice-free locations for surfacing and rendezvous. One of the most exciting aspects of this push toward automated Arctic observation is that the workflow can help democratize access to information, making it easier than ever to engage scientists.
Hi, could you unmute your microphone, please? You are mute to air. If you can unmute your microphone, please. Thank you.
Hello, can you hear me? Hello?
Please continue, Rich.
I'm sorry, there appears to have been an issue with the microphone.
Rich, we have you back. We can hear you if you can continue.
Okay, I apologize for the interruption. I'd like to say, first of all, good afternoon. And David, thank you for the introduction. It's an honor to be here virtually.
Rich,
Yes.
we got most of your presentation. It just cut out at the end. It only cut out for like the last minute or so.
Okay.
A little further along.
Okay.
Yep, keep going. This is where we lost you. Right.
Okay.
Perfect.
Great. So just to recap what's showing here, this is a video showing how a Squiddle user is learning how to label the data. And this process not only improves science literacy, but also advances the scientific process itself by crowdsourcing analysis of large data sets. And this helps us to actively monitor and identify environmental change. And Probably the most exciting aspect of these open access tools is that they provide direct, easily accessible mechanisms for incorporating local knowledge into environmental models and analysis. And I'd like to close by thanking the National Science Foundation, NASA, the National Ocean Partnership Program, and the Schmidt Institute for supporting much of the research that I've shown here. And finally, thank you for your attention.
Thank you so much, Rich. And that was fascinating, and we appreciate you adjusting to the slight technical hiccup. So I'd like to start with a quick question to Karen that I'll then extend to the rest of the panelists about communication. So you had this amazing experience that you told us about, and clearly there's a compelling story there. What do you find are the most compelling ways, the most interesting ways to share that, to share the story of Arctic climate change with a broader audience?
I very much enjoyed talking about it with a variety of different audiences. For example, school groups are great to talk to, especially when you're talking about going out on a ship and you can bring your cold weather gear and they can all try it on, and that works really, really well. So that when you can have a more personal touch it's a much more effective than when you're actually, it's like, for example, speaking right now to an unknown audience. And also, scientific conferences are great, but that's not the very broad audience. And I've also done a lot of communication speaking to local Alaskan communities, particularly on the North Slope, which is where another whole big aspect of my work has been done. And I've really enjoyed that too. And I love getting the questions back from the community members because they make me think about my science in a different way. And so that's kind of two different audiences that I've really enjoyed interacting with, and it's really been the smaller groups and interacting with them personally that have been really valuable.
I extend the question to the rest of our panelists as well, if anyone has thoughts on the most effective ways to communicate Arctic climate change.
Well,
Rachel,
I guess
I'd
I'd like to chime in, and I guess I think one really important thing is I think also just collaboration. Like, we can all communicate as effectively as we can as individuals, but I think it's really powerful when we kind of work together across different communities. I'm really glad that Darcy was able to join us today, because obviously I was talking about permafrost thaw, and I showed some graphs and things, and and that's fine, but it's really, I think, valuable to also have the images and the different kind of the different ways of viewing that issue and communicating that issue as well. So I think it's something that for all of us, the more that we can work together to do that, and also with all of our audiences as well, whether we're talking to school groups or to activists, I think that kind of two-way exchange of that information and saying, what is it that you need from us? How can we support you? We're all on the same team and trying to do the same thing. So I think keeping that dialogue open is critical.
Great. Darcy, please.
Yeah, thank you. In terms of effectively communicating climate change, I think there are a multitude of ways that we can do that. I think as scientists, we're trained pretty easily to publish papers, and that's one form of communication, but that's quite frequently only for one audience, which is the scientific community, which is great, but there are multiple ways to communicate science, as we all know. I think showing photos is a great way to communicate your research in a way that people are going to understand. It's really easy to write a paper and then send it off to the tribe that you were working with, or to the locals that you were working with, but I mean, it's in a language that they don't understand. For example, if an astrophysicist were to send me a paper, I wouldn't understand a thing in it unless we have a conversation. So I think having those conversations outside of the formal venues and outside of the formal events that take place is really where a lot of the change happens. And I think that just having different ways of communication, having a community meeting, going out to dinner, I mean, that's where a lot of the work happens, in my opinion. And I think those are the most effective ways, in my experience, to communicate the real impacts of climate change, which are very real. It's very easy to look at a graph and see that it's going down or it's going up, but it's very different to see an entire community underwater as a result of those lines going up or down. So it's, I think it's really sobering to understand the very real lives that are being impacted by these graphs and by the work that we do.
Absolutely.
One of the things that is a real challenge for working in the Arctic and doing science in the Arctic is that many people feel that the Arctic is entirely removed, and perhaps the systems we're working on, the landscapes that we're talking about, are not something that they're familiar with or that feel accessible to them. So I like to try to bring people along with me. I consider myself as a scientist, as an explorer first. I think many of the panel here would probably agree with that way of thinking about what we're doing. We travel to places often where no one has been before. We come with questions and tools, but also a sense of wonder and discovery. And I like to try to bring that back to audiences, whether it's students, other scientists, policymakers, or the general public. Greenland is an extraordinary place. I don't think anyone has traveled there and seen the vastness of the ice sheet and the changes before their eyes and not been touched forever. I wish that anyone who has a role to play in charting our future could go and experience that for themselves. I think that we would very quickly realize the changes that are necessary. But also there is embedded in Greenland and all of the change and the worry is an extraordinarily beautiful landscape, unlike anything we've seen. And it really saddens me to think of the loss of these landscapes, and as well as the impact on the local communities, as well as the impact far afield when this ice is lost and communities around the world are submerged. But also, we have to think of it as just an extraordinarily beautiful landscape, the blues and the whites and the colors, and I like to share that wonder as well and do my small part to help people fall in love with the Arctic and with ice.
Rich, did you want to jump in on that question, Rich?
I would say that from my perspective, one of the most exciting aspects is coupling the technology with local communities so that we can engage that citizen science. It really is a force multiplier. And from the technology side, one of the kind of focal points is to make the technology sort of melt into the background so that it's easily accessible, and so that, for example, indigenous communities can use these tools to help actively manage their regions, the environments in their regions, because when you get down to it, there are no groups that are better at that than these people who live there and have a vested interest in the well-being of the environment there.
Absolutely. So I'm going to pivot to more of a scientifically focused question, and I'll open this up to whoever wants to start it. You've all explained a lot of what we do know about Arctic climate change, but what more do we need to know? What more research is needed? Where is the kind of next big challenge and hurdle in terms of our understanding? I'll put that out to everyone.
I'm happy to start. So a lot of what we understand now about how polar ice sheets work, and Greenland in particular, really has come from observational and technological advances just in the last decade or 2 decades. And I think that we need to keep that in mind going forward. What are the observations we need to make and the technology that we're going to need going forward to continue to monitor the ice sheet and measure its changes, measure its response to climate? Greenland is very inaccessible. In particular, underneath the Greenland ice sheet, we have no way of making measurements or detecting change except through sort of extraordinarily long and expensive campaigns to drill, for example, a single hole through the ice and put an instrument down. So there's a lot we don't understand about what's happening beneath the bottom of the ice sheet, where that water is flowing between ice and bedrock out to the sea. Yet that's a critically important environment in terms of putting understanding into models that will help us predict the future flow of ice and that sea level curve that has those big question marks around it. So I think a lot of focus needs to be there. And we need continued investment in the observation systems that we have for both the Greenland and the Antarctic ice sheet. We can learn a lot by boots on the ground, and in particular for looking back in time through ice cores or paleoclimatology. There's no real way to do that without going onto the ground. But if we want to study the ice sheet as a whole, we can really only do that from satellites. And that takes a tremendous investment and continued investment of time and resources.
Absolutely. Yeah, absolutely. And we've seen, as you said, the benefit of that in our increased understanding. I can move questions, or if anyone else wants to jump in on that.
I'm happy to add to that briefly. I think we could probably talk about that for the rest of the day. I think we do, of course, as you say, we've talked about the things that we do know, and of course there is a lot that we do know. I don't want to sort of denigrate that, but nonetheless, there certainly are still a lot of gaps and a lot more work to do. And I think it's useful sometimes to remember that there's more CO2 in the atmosphere now than there ever has been before in human history. So we're very much off the map, and that poses real challenges in terms of predicting into the future. And on top of that, of course, as I mentioned in my talk, across the terrestrial Arctic, we really, in terms of that quantitative data that we need to be putting into these models, it's sparse, and it's sparse in terms of across space, it's sparse in terms of the variables that we need, and that means that often we do have to sort of make these generalizations across large areas of the Arctic. And the Arctic in particular is a region that varies a lot, so that's it's a very challenging thing to do. So there's a lot more work to be done in terms of scaling up that monitoring, having monitoring at a greater spatial resolution, collaborating together more effectively to get that data. And really just carrying on the work of putting that into models and trying to untangle some of that complexity that we face.
Absolutely.
Yeah, if I may. I think to follow up on that, I'm glad that we're talking about the global aspect of all of this, because it's huge. The implications that are going to happen with, the Greenland ice sheet and with permafrost thaw. But I think something to highlight here is that we're seeing the changes now. The Arctic are seeing the changes now, and the residents that live there and reside there and live off the land there are seeing the changes now, and they have for many, many years. I think the question is a really interesting one as a trained Western scientist and as an Indigenous person, because there's a lot that Western scientists don't know, I think, that Indigenous people do know. So I think it's a matter of working together to translate to translate the Indigenous knowledge that's been passed down for generations and generations and generations. We live on this land. We've lived there forever, since time immemorial. We have extensive knowledge. If it was in the form of Western science, it would be the richest data set in the world. But since it's traditional knowledge and it's passed down through stories and observations, all of a sudden it's invalid, and people are scared and don't trust what Indigenous people have to say. And Indigenous people are the richest data set in the world if you just sit down and have tea with them or talk with them. So I think in terms of what we don't know as Western scientists, there's a lot. But in terms of my Indigenous side, if you will, just go and talk to an elder. Go and reach out to the community and have a community meeting, listen to them as a scientist, just be comfortable with being uncomfortable in a space where you're the minority, and just realize that we have hundreds of thousands of years of data in our brain, and I think that the quality and the validity of your research can only increase by working with Indigenous communities.
Absolutely. Karen, and then we'll go over to Rich.
I think a couple of people have said we still don't know very much, which is absolutely true, and I think we alluded to that. And I think I've got two sort of takeaways on that, and one of them is we need to continue observing so that we can understand, and one of the best ways to do that is through collaboration, whether it be international collaboration, such as for the Western science programs that I referred to, or collaboration with Native peoples who can tell us, who we can work with to unearth that incredible wealth of knowledge that they hold. And then returning again to Sarah talking about the new technologies, I think it's very interesting that, or very important to realize that a lot of what we can do, what I can do as a biological oceanographer when I'm out there working with my animals, cannot yet be done with technology. And so we're developing all these wonderful ways of getting under the ocean, under the sea ice, but yet we can't sense yet a lot of the stuff that I would need to know. And so working on improved sensing as well as improved access, I think, is really important to trying to unearth what's going on underneath that sea ice. Or unearth.
Rich, I imagine your comments might be might dovetail nicely with what Karen was just talking about.
Sure. I see really two main observational gaps, and the first one really Karen hit the nail on the head there, and it's creating these integrated models where we can take these disparate data sets or sensing modalities and bring them together into a kind of unified model. This is where the technology really isn't there yet. Now, another kind of gap technologically is being able to sense during extreme weather events. This is where, as a human, you really don't want to be out in the field. And in the Arctic in particular, these extreme weather events tend to drive, they are forcing functions for things like ice breakup, and being able to send automated systems out to collect that data and observe exactly what's happening then is critically important. And we're just now starting to get to that point.
Great. So we're almost at time. I want to end with one very COP-specific question, Rachel, for you, if you don't mind, focused on loss and damage. So within the context of the negotiations, the conversations here at COP26, loss and damage is an issue. Given what we've heard about the observed changes, about the observed impacts in the Arctic, can you tell us just a little bit in the minutes we have remaining about how Arctic impacts figure into the global loss and damage conversation?
Yeah, it's an interesting question. It's a challenging one, but it's important because, of course, as we've sort of discussed and as Darcy has sort of shared so eloquently, this is something that is very much a current reality in the Arctic and has been for a long time and will be, of course, for even longer. And by loss and damage, we mean these unavoided impacts of climate change, which, of course, is exactly what we've been talking about there. And in the context of the UNFCCC and in the context of COP, therefore, of course, the challenge is loss and damage is a critically important part of all these conversations we're having. It's something that focuses on developing countries. So for the Arctic, it's there's that kind of element of complexity there. But regardless of how we sort of approach that and how we move forward in the context of the UNFCCC, it's something that we very much need to be having a conversation about. At the moment, Arctic communities are really falling through the cracks in terms of the international conversation around loss and damage. And so that is something that we really should be talking about more already. And yeah, it's a critically important issue.
So with that, I'd like to thank our panelists. Thank you so much for joining us in person. Rich, thank you for joining us from Falmouth, Massachusetts. I'd like to thank everyone who tuned in from wherever you are. And we will rejoin the COP26 conference and hope to see firsthand some real progress in terms of policy negotiations. Thank you.